This is a problem involving a bubble inside of a liquid. So I've got some gas inside of a liquid. At the interface between the gas and the liquid, that's where surface tension develops. And because of that surface tension, that acts to squeeze this bubble, and it creates a higher pressure inside than outside. So in this case, I've got gas, I've got a liquid, and I've written that delta P is the pressure of the gas minus the pressure of the liquid. You could also look at a water droplet. In the case of a water droplet, you'd have liquid, you'd have gas on the outside, and so delta P would be the pressure of the liquid minus the pressure of the gas. The same geometry works for whether it's a gas or a gas bubble or a liquid droplet, but you would need to reverse the sort of labeling of the pressures. Okay, so physically we have a handle on what's going on here. We've got this bubble of gas. It's being squeezed by surface tension. Because of that squeezing, we've got a higher pressure inside the bubble. So how do we do turn this into a fluid mechanics problem? Well, we bring in the idea of force balances. And because this is a radial problem, radial coordinates, actually spherical coordinates, it's tempting to sort of think, oh my gosh, I've got to work this out in some spherical coordinates. But you don't, actually. There's a really clever way to think about the force balance, and that is to make a slice right through the center of the bubble, and to think about removing the bottom half of that bubble and doing a force balance in just the vertical direction. Because once you've sliced it horizontally right through the middle, all the forces are perfectly vertical. So with that in mind, we can draw a free body diagram of this bubble, at least half the bubble. Okay? And now what's happening, since we've removed the bottom half, we need to put in equivalent forces. And so the equivalent forces are going to be the surface tension pulling downwards on the perimeter of that interface. And then you've got the pressure inside the bubble, which is going to be pushing up inside. Okay? So now we've set up a problem nicely because we have two forces working against each other. We've got the force associated with the fluid pressure pushing upwards into the bubble, and we've got the force associated with surface tension pulling downwards around the perimeter of the bubble. Okay, so at this point, we've drawn a diagram, we visualized the problem. Now we sort of need to identify all relevant principles and laws. So first thing we can write down is that the sum of the forces in the vertical are going to equal 0. So that means that the force due to pressure is going to equal the force due to surface tension. So that's the first thing. The next thing we can do is relate this delta P to a force. So we know the force due to pressure is going to be equal to some increase in pressure times the area over which that pressure is acting. We know that's just equal to pi over 4 d squared. Okay? So the next thing we can do is think about this force due to surface tension. That's going to be equal to the surface tension multiplied by the length over which that surface tension acts. So that's sigma times the length of the circumference. Okay, and that's just equal to sigma times pi times d. Okay, so now I can substitute these expressions in. I'm moving on to sort of solve the problem analytically. And when we do that, we can write that delta P times pi over 4 d squared must be equal to sigma times pi times d. Okay, and now I can simplify. One of the d's goes away, the pi goes away, and I can rewrite this in terms of an equation for the pressure or an equation for the surface tension. Let's go with pressure. So I'll write this as delta P is just equal to 4 times sigma over the diameter. Okay, so then we can ask, well, does this make sense? What this is saying is that as surface tension increases, the pressure inside the bubble will increase. That makes sense. If this is going to squeeze harder, the pressure is going to go up more. It also says that as the diameter of the bubble gets bigger, delta P gets smaller. And that's related to the fact that as the bubble gets bigger, the curvature gets smaller. And so the transfer of force is reduced. So that's how we go through this problem. Identifying a dry diagram, identifying relevant principles and laws, solving it analytically, and then if I were to give you a magnitude of a surface tension, a diameter, you could solve for pressure. Surface tension is going to be linked to a fluid, gas, or solid interface. So surface tension value is typically something you're going to look up in a table. It's going to be dependent on temperature, but in the fluid gas combination. Okay.